In this video, I will be discussing the concept of the center of mass. We've been using this concept already throughout the course when we drew our motion maps. For example, the image I just posted on your screen is a picture of a crate that's sliding down a smooth, frictionless surface. What we did is we decided to represent this crate as a single point, as shown by these black dots. That point, all along, was called the center of mass. We also used the center of mass when we drew our free body diagrams. Here's an example of this situation. We have a car being pulled by a rope. And we drew the car, that system of the car, as a single point. Again, we assumed all of the mass was concentrated at one single point called the center of mass. Up until now in the course, we've assumed that all of our objects can be considered as point masses, where we represent the mass of that object as one single point in space. We have only really considered what we call translational motion. That's shown over here in figure A, where the diver is jumping off a board in a very rigid way without rotating. Soon in the next chapter, we're going to start to look at rotational motion, where a body rotates about a fixed point. If you move to the bottom of your notes, you're going to see down in the bottom a situation where we have something that is just simply rotating about a center point. So this particular point right here in the middle, I'm going to label that as CM, which stands for the center of mass. Every other point around that rigid rod is actually rotating in a circle around that fixed point. This is known as rotational motion. If we go back up to the top of the page here, where we see the diving question, we now look at case B. Now in this particular case, we could see that she's actually rotating and also translating. So this is a, let's call it a combination motion. In this particular case, we have both translational and also rotational. You can see in both cases there's a little black dot shown on her body. This is again known as the center of mass. That center of mass in both scenarios, whether she's translating or she's rotating, that center of mass follows the same path, that parabolic path that you can see here. If you skip ahead in your notes a little bit, on the last page of your notes you can see a picture of a baseball player throwing a baseball bat in the air. Now, if you were to throw just simply a baseball in the air, it would follow this beautiful path because the baseball would more or less be like a point mass. But if you were to toss like a baseball bat, you can see that really only one particular point, this point right here, that center of mass, is the only one that's actually going to follow that parabolic trajectory. Every other point, like the end of the bat, will actually follow and rotate about the center of mass, and it's not going to be that nice smooth parabolic path. Here's another example of a combination of motion, of translational and rotational motion. And here we have a wrench that is being kicked or just given maybe a hit with a hammer, just like we showed in class, where the wrench is actually rotating about that center of mass shown here in red, but that center of mass is following a nice straight line path. The figure of the wrench shows that the wrench was acted on by a zero net force. So it is translating and rotating along a horizontal surface. But notice that center of mass, marked with that little red X, is actually moving in a straight line at constant velocity. And it's not accelerating because the net force on the system is zero. Let's take a look at the conceptual example down below at the very end of your notes. Here we have a rocket that's shot in the air, but at the moment when it reaches its top point, it breaks into two pieces. The back end of the piece just falls straight down. That means that the velocity of this piece right at this particular point would be zero. The other piece too would have to move off, and you'll notice that it follows a further path here too, twice the distance from this object here. If this whole thing as a combination is traveling at a velocity of v, part 2 is now going to travel at a velocity of 2v. Now you might be wondering, why would that be? Well, let's say that mass of that rocket is m. Well, then this piece, let's say, is half that mass, and this is half that mass. To compensate for this velocity stopping and this being half the mass, then it has to go at twice the velocity. But notice, again, the path of the center of mass would be right along here. It'd be much more complicated, let's say, if this didn't simply just stop and fall straight down. Suppose this piece 1 fired straight up. Then it would be a much more complicated problem to deal with. So the next question you might be wondering is, how does one go about locating the center of mass for an object or a system of objects? Well, the easiest kind of object to deal with would be something that's highly symmetric. You go down to the bottom of your notes. If you happen to have an object that is highly symmetric, uniform density all the way throughout, then the simplest way to find it in this type of object is just to find the geometric center of that object. We call that in geometry the centroid. So if you have a solid block, and this rectangular block could be just in the geometric center of that block, or the cylinder would be in the geometric center of that cylinder. If you have this torus or a donut, then it's in the geometric center. So notice that you could have a center of mass in a location where you actually don't have any mass. There are all sorts of interesting examples that show you the center of mass. For example, in class I showed you that little bird that I was balancing on my finger. There's also a boomerang. And then the soccer ball, the center of mass is there. And then if you have an object that you want to find the center of mass, where the mass is not distributed evenly, the key thing that you can do is just simply try to support it under with your finger underneath it. And if your finger can balance it perfectly at that location, then the center mass is just straight above it. So as long as the object's near the surface of the Earth, in any orientation, it can be supported directly below the center of mass. And you may have noted in the images that you have some things that were mentioned, center of gravity and center of mass, kind of in the same location. And more or less they are, but sometimes they are a little bit different. The center of mass and center of gravity could be a little bit different if the force of gravity does definitely differ, say from, let's say, this heavy solid block. If there's more force of gravity at the bottom part than there is at the top of part if it's resting on the ground, then the center of gravity is going to be slightly lower. But more or less in all our situations, we could say the center of mass and the center of gravity are at the same location. In the next page, I go over some examples about the center of mass and center of gravity. And I also talk at the bottom of that page, I show you how one could determine the center of mass experimentally. Now, if you were to hang what we call a plumb line from different locations of a regularly shaped object, and you find the intersection of these plumb lines, then that particular point is called the center of mass. So the concept of center of mass and center of gravity are very, very similar. The difference is just simply that the center of gravity of an object is the point where the force of gravity can be considered to be acting at that location. So really the force due to gravity is acting at that point. Whereas the center of mass is really the average or the weighted average of all the mass of that object, where that could be assumed to be concentrated at that point. The center of mass and center of gravity have all sorts of key applications. Many car manufacturers, for example, try to lower the center of mass of a car to make it more stable when it makes turns. Let's take a look at an example for astronomy. Here's an astronomy example. We have the Earth and Moon system, and we have the Moon orbiting around the Earth. You may notice, if I put the grid on here, that the Earth is actually wobbling. And the reason for that is because the center of mass of this Moon-Earth system is not in the geometric center of the Earth. It's slightly towards the Moon. So if I were to stop the Moon right here, it would be just a little bit off-center towards the Earth. And so therefore, the Earth is actually rotating about the center of mass. Let me give you another example. Here's another model of a solar system where you have the sun or star and a planet. And in this particular case, the sun is a mass of 200 units, where body 2 is 20 units, or 10 units. It's still significant. And if I were to trace out the path and play this, you could see that literally this sun is wobbling. And so there is a center of mass of this this solar system to be about right there. Here's a really cool one. This is a binary star system. So I'll press start here, you can see that. And now you have several objects that are revolving around each other, and yet they're revolving around one central location, which is called the center of mass. Here's another set of animations that I found on the internet that actually show a beautiful example of the center of mass. You can see the center of mass shown in here in this dark red X, and you can see that these bodies are revolving around that particular fixed location. That location, they call it, that center of mass, they actually call it the barycenter. All right, Well, that's about it. I've rambled on enough about center of mass, and I think you can now start to look at how to calculate the center of mass in the next video.